Okay, we're going to be looking at the questions in exercise 15.2. That should be on page 166 of your textbook. And it's a little bit tricky because they haven't given you all the information in the actual question. They ask you to look above in the blue box. If you see right at the start, it says values for C and L for the heat capacities and latent heats are given before in the problems above. So just if that's your textbook there's the questions we're going to be looking at today. And here's the information you're going to need to complete them. I know that's still out of focus, but it'll improve. Okay, so all of these are basically quantifying how much heat is needed to do a number of different things, like melting a block of ice or turning a liquid to a gas or vice versa, or raising temperatures and lowering temperatures. So it starts off very easy. Now what I'm going to do is I'm going to do all the odd numbered questions between 1 and 10. I'm going to do 1, 3, 5, 7, and 9. And I'm going to ask you guys to try yourselves 2, 4, 6, 8, and 10. And then the later ones, the more difficult ones, we'll tackle together in a live class, 11 to 13. They're a little bit trickier. But for now, we're going to kind of go step by step. Hopefully, it shouldn't get too bad. Okay, so the equation we're kind of going to use all the time here is for a changing state, the energy needed is the mass of whatever you're talking about times the latent heat of whatever you're talking about. And from last time, we might need later on for raising and increasing temperatures, the specific heat capacity formula, the energy transferred is equal to the mass times the heat capacity of the substance times the change in temperature that you're looking for. We probably won't need that one for a while, but we'll leave them up there anyway. Okay, so let's make a start. Question 1. How much heat energy is needed to completely convert 10 kilograms of ice at 0 degrees to water at 0 degrees? There's no change of state here. We're just taking 10 kilograms, so the mass is 10 kilos. From above, we know that because we're dealing with ice turning to water, we're looking for the heat. The latent one we're looking for here is the heat of latent fusion for ice. And that is 3.3 by 10 to the power of 5 joules per kilogram. All right, straightforward enough. Just plug the numbers in this time. So the energy required, Q, is equal to the mass of 10 kgs multiplied by the latent heat, the latent heat of fusion for ice, 3.3 by 10 to the 5 joules per kilogram. So we don't even need a calculator really for this one. 10 by 3.3 is 33 by 10 to the power of 5. And let's look at our units. Kilograms by kilograms to the minus 1, they're going to cancel each other out, leaving us with just joules. Now, if you're comfortable with scientific notation, the kind of slight improvement of this is to convert this into a number between 1 and 9. So let's say that's 3.3 by 10 to the power of 6 joules. Same number, just written slightly differently. Now, if you're not too comfortable with powers of 10 yet, don't worry about it too much. It's just kind of a convention. We'll be talking a bit more later on. But that's not the rest of the lesson. So first one, straightforward enough. Okay, no surprises there. Let's try the third. Remember, I'm skipping all the even numbered ones because you guys are going to try them yourselves. What's the maximum amount of ice at 0 degrees Celsius that can be melted by 1 megajoule of heat energy? Megajoule. All right, so 1 megajoule is equal to 1,000,000 joules. Or if you want to write that in scientific notation, 1 by 10 to the 6 joules. Okay, so what's the maximum amount of ice that you could melt? Well, let's go to our formula. So the energy is equal to mass times the latent heat of fusion. We're looking for the mass. How much mass can this energy melt? So let's divide Q by the L, will give us our mass. Okay, now it's just a matter of putting in our numbers. So our energy was 1,000,000 joules. I'm going to write that in scientific notation actually. So it's 1 by 10 to the 6 joules divided by the latent heat of fusion of ice, which is 3.3 by 10 to the 5 joules. Now, I've used a calculator to get the answer, but let's just look at the joules per kilogram. That's the whole point of what we're doing, is looking for mass. That's a silly mistake on my part. The joules are going to cancel each other out. 10 to the power of 5 is going to cancel out most of these except for one of the 10s. Okay, so it's just like saying 10. So like 10 joules divided by, 10 divided by 3.3 kilograms to the minus 1. And that is going to give you an answer of 3.03 kilograms. And again, trust your calculator if you don't trust my weird maths there. But as you get more comfortable with powers of 10, you'll be able to try a few little tricks like that. Just helps speed things up sometimes. But always trust your calculator in the first instance. Okay, so 3.03 kilos is the maximum amount of ice that 1 megajoule can melt. All right, that's question 3. I should be labeling these actually so we can keep track. So let's see, let's do number 5 next. Okay, so for number 5, how much heat energy is needed to completely convert 80 grams of water at 100 degrees Celsius to steam at 100 degrees? Okay, well, first off, grams are no good. They're not our friend. 80 grams is 0.08 kgs. Kilograms are our friend. Let's go with our equation. Heat. The heat energy needed is the mass times the latent heat. And this time we're converting water to steam. Now, they're both at 100 degrees, which is great, so we don't need to worry about increasing the temperature, just the energy needed to break apart the water, to separate the water molecules from each other and convert it into steam, to overcome the force of attraction between the water molecules. Okay, so we don't have to worry about increasing the temperature. This is just our basic formula here. So how much heat energy is needed? Well, that is the mass, which is 0.08 kgs, times the latent heat. At this time, we're going from water to steam. So we're not using the latent heat of fusion of ice. We're the latent heat of vaporization of water, so turning water into a vapor. So 0.008 times 2.3 by 10 to the 6 joules per kilo. Let's just have the brackets keep a little bit here. Okay, so when we multiply these out, that kilogram will cancel with this kilogram, leaving us our final answer in joules. And again, I've cheated a little bit. I've done it on my calculator. I've got 0.184 by 10 to the power 6 joules. Or another way of saying that, that's like saying 1.84 by 10 to the power 5 joules. So that's how much energy is needed to completely convert 80 grams of water to steam water to steam without changing the temperature. That's number 5. Okay, there's a slight step up in difficulty now for number 7. So let's just check for a moment. How much heat energy is needed to convert 1 kilograms of ice at 0 degrees Celsius to steam at 100? Okay, so this is a little trickier. So let's just recap what we're doing here before we tackle this. We're going to start with a big block of ice, 1 kilo. And first off, we need to melt it. So we're going to need some energy to melt it first, which will turn it into water. And then that water is going to be at 0 degrees. We're going to need to increase that water's temperature. So let's just say warm the water. And we're going to need some amount of energy to do that. And then we're also going to need some energy to turn it into steam. So overall here, we've got 3 things we need to figure out. Let's write that a little bit neater. So we need energy to melt the ice plus energy to increase the temperature of the water from 0 to 100 degrees Celsius. And then we also need some energy to turn the water to steam. Okay, so this is a little bit more involved than the previous ones. So let's go for energy to melt the ice first. So what kind of numbers were we talking about? They said 1 kilogram. Oh, that's nice. So for this one, we're going to use Q is equal to ml. So that's the mass is 1 kilogram of the ice times the latent heat of fusion for ice, which is 3.3 by 10 to the 5 joules, plus, I'm actually just going to switch pen here so we can maybe keep this a little bit easier to separate. Plus for the energy to heat the water, remember from our last lessons, Q is equal to mc by delta theta, so the mass of 1 kilogram, times the heat capacity of water, which was 4180 joules per kilogram per Kelvin, times the temperature difference, which was 100 Kelvin. I switch back to blue for this last one over here. I'm going to just take it down here. The energy to turn the water into the ice then is the 1 kilogram of mass times this latent heat of fusion, the latent heat of vaporization for water, which I'm going to put it in brackets here because I'm running out of room, is 2.3 by 10 to the 6 joules per kilogram. I know my units are a bit messy there just because I'm running out of space. In fact, a little bit better. Okay, so 1 kilogram by this is just, let's tidy this up a little bit, 3.3 by 10 to the 5 joules, the energy needed to melt the ice, plus 4180, and then don't forget the 100, so 418000 joules to heat the water from 0 to 100 degrees Celsius. And then finally, to convert that water into steam, we need 2.3 by 10 to the 6 joules. Well, we just got to add these three numbers together. And again, I've cheated a little bit, and I've done it earlier on. And I got 304,800 joules. And that's good enough as a final answer. I mean, that's kind of a winner right there. But if you want to just go the extra little step, if you notice it's such a big number, we could actually use megajoules here because there's 1, 2, 3, 4, 5, 6. This is like 3 and a bit megajoules. Remembering that a megajoule is a million. So that's 3.048 megajoules if you wanted to be a little bit neater with it. But to be honest, that's not the main thrust. That answer's just fine as it is. Okay, finally, let's look at question 9. How much steam at 100 degrees Celsius must be added to 60 grams of ice at 0 to just bring the resulting mixture to 100 degrees? Okay, so let's start off with the ice. They've given us, first curveball, as they said, 60 grams. So 60 grams of ice, that's like saying 0.06 kilograms of ice. So what do we need to do here? First off, what are we going to need? We're going to need some heat energy to melt the ice. And then we're also going to need more heat energy to increase the temperature of the ice, the water, because now it's melted, to warm the water from 0 degrees Celsius to 100. And the final step, because they're looking for oh no, that's it. Is it that easy? Okay, so let me try that again. Okay, for the final question, they've tried to mix things up, but they haven't talked about how much energy, they're talking about how much steam do you need. Okay, it's a little bit trickier than it looks actually. So first off, let's see how much energy is needed, and then we'll worry about the steam. So when I say how much energy is needed, I mean energy to convert 60 grams of ice to water at 100 degrees Celsius. Because it says to just bring it to 100. They don't want it to go into steam. So okay, first off, let's look at the first curveball. 60 grams, no good. 60 grams is equal to 0.06 kg. That's more like it. Okay, what we're going to have to do here is, first we're going to have to figure out how much heat is needed to melt the ice. And then we're also going to need heat to bring that ice, or sorry, to bring that water, because it's melted now, from 0 Celsius to 100 Celsius. Okay, so first off, let's figure out how much heat is going to be needed to do that. Okay, so we have, for the first one, we have our mass times our latent heat. And for this one, we're going to need our mass times the heat capacity times the change in temperature. So the mass is 0.06 kg, and the latent heat of fusion for ice is 3.3 by 10 to the power of 5 joules per kilogram. Joules per kilogram. Oops. And the second part, the second bit of energy we need, is the mass, which is 0.06 kg, multiplied by the heat capacity of water, 4180 joules per kilogram per Kelvin. And that's also, I'm going to write a rinse to say multiplied by the change in temperature, which was 100 degrees Kelvin. Okay, so again, I've cheated a little bit and worked it out. When you put these numbers in, the units are going to cancel again, kilograms to kilograms, giving us just joules. And I calculated before, I got 198 100 joules for the first bit of energy we need to melt the ice, and the second bit of energy we need worked out as being 25080 joules. So when you add them together, the total energy we're going to need here is 44880 joules. Now we're most of the way there to our answer, but not quite all the way yet. So that's the total amount of energy we need to melt that 60 grams of ice and heat it up to 100 degrees Celsius. But the question they were asking is how much steam will we need to do that? Okay, so let's get rid of all this. Okay, so 44880 joules. That's the magic number here. That's the amount of energy we need. So how much steam do we need? Well, let's go back to Q is M times L. We know what Q is. We know it's 44,880 joules. We know the latent heat of vaporization for water, so we can easily find what M is. So Q divided by L will give us our mass. So 44880 joules divided by the latent heat of vaporization of water, which is 2.3 by 10 to the 6 joules per kilogram, will give us 0.0195 kg. Really tiring on that. So the amount of steam we need to melt that ice and heat it up is 0.0195 kilograms of steam. Okay,